Hey everyone, it's Bradley Bush again with another algebra video. Today we're talking about the factor theorem. Our to-do list, first off, we'll talk about, well, what is the factor theorem? And then I'll give you a worked example where we use the factor theorem. I'll also put the timestamps in the video description so you can skip ahead if you want. What is the factor theorem? Well, here we have it. If we say f is our polynomial, then if we take some value, some constant on the x-axis, some x value, we call that x value c, and we plug it into the function and we get 0 out, then we know that x minus that same x value c, x minus c is a factor of our polynomial. We're guaranteed. If f of c equals 0, meaning we say x equals 5, if x equals, or say c equals 5, sorry. If c equals 5 and we plug 5 into our function and we get 0 out, then x minus 5 we know is a factor of f, meaning we could factor it out if we were trying to factor that polynomial. And b is just the converse. So if x minus c is a factor, if we know that that's true, because say we find out because we factor, then we know that we're guaranteed that if we plug that value c into the function, we'd get 0 out. So you might be thinking, isn't that kind of overkill? Why do we have both of these statements? Don't we just need one of them? Because they say the same thing. Well, mathematics is kind of funny that way because they actually don't say the same thing. Let me give you an example. Let's say you have an event, and we call that event A. Say A is the event that it's raining outside, and B is the event that the grass is wet in our yard. So if we have two statements, if we have two if-then statements, the first one is if A, then B. Well, if A is true, so if it's raining outside, then we're guaranteed that our grass is going to be wet, right? We know it. There isn't any way, unless you have all of your grass covered by a big canopy, your grass is going to be wet. So if A is true, so if it's raining outside, we're guaranteed that our grass is going to be wet. Mathematically, we write A arrow B for that if statement, if-then statement. So if A is true, we're guaranteed that B is true. But that doesn't necessarily mean that the reverse works, right? Because if the grass is wet, if B is true, do we know that it's wet because it was raining? Well, I can think of a million different reasons why the grass could be wet, and none of them are rain. I could have turned on the sprinklers. I could have washed my car on the lawn. I could have had a water balloon fight and had the hose running. I mean, I could have had a leak in my sprinklers. I mean, there are a million reasons why your grass could be wet, right? And it isn't necessarily guaranteed that it's because of the rain. So if you have two statements, A and B, two occurrences, two things that happen, if you have an if-then statement, it's really only one way. So if A, then B, if you know that is true, if A is true, then you guarantee B. That doesn't necessarily mean that if you have B happen, that A is going to happen. So that's why we have to have two of these up here, because the first one that we call A, little a, this one is actually the statement if A then B. And the second one, little b, is the statement if B then A. So what this factor theorem is saying is both of those are true. You know that both of those are true. So if you pick some value c and you plug it into the function and you get 0 out, you're guaranteed that x minus c is a factor of f. And if you know by chance, and actually once you know that, you don't even need to know anything else because you know the revert that if you go backwards it works as well. That's what this theorem tells you. Both of those if-then statements hold. So just as a reminder, if some value you plug into your function c is equal to 0, then that means x equals c is an x-intercept. Don't forget that. because that's all very connected. So the factor theorem is actually pretty powerful. It's very complete. It covers both of these scenarios. If A, then B, and if B, then A. Let's do an example here with the factor theorem. So say I'm given the function 2x cubed minus 3x squared minus 11x plus 6 equals 0. This function there. And I say factor that. Well, it kind of looks nasty, right? I guess I could start with factoring by grouping, but I don't even know where I would start because I can't pick two groups of 2 that seem to factor nice. I could pick the 2x cubed and the 6. They both have a 2 common, but then I have a 3x squared and an 11x. I guess I could take an x out of that. But see, it's not gonna work super nicely. It's not gonna be clean. So if we graph this, we see the graph over here in blue on the right hand side. We can see right away that we have some x-intercepts, right? We have -2, we have 1/2, and we have x equals 3. We have those that are x-intercepts. And with their x-intercepts, then what do we know? We know that f of whatever that number is equals 0. So we know that f of -2 equals 0. We know that f of, what's the other one? 1/2 equals 0. And the last one is f of 3. We know that if we put 3 in the function, out would pop 0 because we can see it here in the graph. It's clear right there. I just circled in blue. So by the factor theorem, because we just found out that f of these x values equals 0, we know right away what the factors are. It's x minus whatever that factor is. So then we have x minus -2 is a factor, x minus 1/2 is a factor, and x minus, what's the last one? 3. X minus 3 is a factor. Those are all factors of f, and we just got them all because you can see clearly there are only 3 x-intercepts. So there are only 3 roots, so that's all that we can't have more factors than that. So we can just write it out, actually. Let's do it. If we're writing it out, then that means we could do, what's the first one? X minus a -2, that gives us x plus 2. There's one factor. The second factor is x minus 1/2. So x minus 1/2. And what's the third factor? X minus 3. That's the third factor. X minus 3. And this is all set equal to 0. So that's it. We just factored this equation. That's actually pretty powerful, right? There's only one thing I would add here, and we could change this middle one. We could have written this whole thing like this. X plus 2, 2x minus 1, and x minus 3 equals 0. Either one of those is okay. And you're probably wondering, what? Where did he get that? Well, if we take this, well, first of all, let's take the first one. Let's take this one up here. If we take x minus 1/2 equals 0, because if we set all these equal to 0 to solve for the actual root, we would get this equation here, x minus 1/2 equals 0. If we now just multiplied both sides of the equation by 2, which we can do, right? If you have an equation that's 3 equals 3, and we multiply both sides of the equation by 2, what happens? We get 6 equals 6, which is still a true statement. So we're perfectly valid here. We haven't done anything wrong. The 2 comes in there, and it comes into the second one. And what do we get? We get 2x. 2 times 1/2 gives us -1. And 2 times 0 is 0. So we have another statement here that equals 0. And we can just replace our original x minus 1/2 with 2x minus 1, which is exactly what we did here. If you had been able to factor this, by the way, if you'd factored it, say you had used synthetic division to kind of whittle the factors out and find them, then you would have come up with this second factoring. It would have looked like 2x minus 1. But if you had just used this straight factor theorem the way we did, then you would get, you would come out with the top factoring. But either of those two are accurate and are the answers. Kind of cool, huh? The factor theorem is kind of a cool theorem. Hope you enjoyed it. If you liked it and if it was useful, please leave a comment, subscribe to the channel, and have a good day. Thanks for watching.